The fascinating thing about the eye is that it knows how to tell a story. Now it is left to us to learn the language of the eye so that we can actually understand the story that the eyes are telling. So today we will be speaking about one such stories that the eye tells, nystagmus. Now before we start speaking about nystagmus, however, there are a few concepts that we have to understand. The first of them being this. Now this is the image of the two eyes. Now if we remove the orbital roof and look at the eyeballs from above, this is how the eyeballs look. Now if you can see, this is the eyeball and there are different extraocular muscles attached to the eyeball. Now the reason we have extraocular muscles is so that we can move the eyeball in different directions so that we can keep the visual target in focus. The whole idea of having extraocular movements is so that we can keep our visual target in focus. The visual information from the target of interest should fall on the fovea of the retina so that we have a clear vision of that particular object. So it should be noted that when a person is sleeping, for instance, and all of these extraocular muscles are relaxed, this particular eyeball will tend to lie in this direction. It will lie free in this particular direction, and if you look at both of these eyes together, they will be slightly diverging when a person is sleeping or when all of these muscles are relaxed. So in a sleeping person, if we raise the eyelids, we'll see that the eyeballs are slightly diverging. When all the extraocular muscles are relaxed and they lie along the orbital axis. However, when a person wakes up, both of these eyes align in such a way that the visual axis is parallel to each other. Now, so it is necessary for us to have our visual axis parallel to each other so that the visual information from both of these eyes overlap and there is 3D vision available for us. So it goes without saying that once a person wakes up and wants to look at a particular target, there is some or the other extraocular muscle contracting so that both of these eyes have a parallel visual axis. However, if the extraocular muscles relax completely, the eyes will automatically diverge. They will go back to their resting position because the viscoelastic tissue present within the orbit will make the eyeball go to this particular resting position. This is a very important concept that we have to understand. Now the next concept that we will be speaking about, which I personally find extremely fascinating, is the concept of normal eye movements. Now I will not be speaking about individual eye movements like adduction, abduction, supraduction and all of those movements. I will be speaking about gaze, that is how the eye manages to look together to different visual targets. We will be speaking about these normal eye movements and we will start off with these, but before we do that, I would like to introduce you to a very special person, my cat Cindy, who will be helping us understand this particular concept. So let's presume that I'm sitting in my house and I'm reading a book and suddenly Cindy decides to come and sit next to me. Now, it goes without saying that if she's sitting over there, I'm not going to continue to read. So initially, I was looking at my book and my visual axis. The visual axis of both of my eyes were aligned so that I was looking straight at my book. Now, when Cindy comes over here, obviously, I'm not going to continue to look at my book and my visual axis is going to turn laterally towards her. That is, she came and sat and immediately I turned both of my eyes from looking anteriorly to looking laterally towards her. How exactly did I manage to do that? I did this with something called saccades. Now saccades is a normal eye movement. What exactly is a saccade? It is a conjugate rapid eye movement. It has to be understood over here that this particular eye movement happens together. Both of our eyes move together at once from one visual target to another visual target. It is a conjugate and rapid eye movement. It can be voluntary or it can be reflex. Now if I did not know that Cindy was sitting there and suddenly she jumped over there and suddenly by reflex I looked towards her, that would be a reflex saccade. Now instead, if I knew she was sitting over there for a long time and I was continuing to read my book, but in between the reading I decide to voluntarily look at her, that would be a voluntary saccade. Now this particular eye movement is present at birth and it can vary from 30 to 700 degree per second. It can be extremely rapid. It can go all the way till 700 degree at once per second. The latency can be anywhere between 200 to 250 milliseconds from the time we receive the impulse to the time both of our eyeballs turn towards the target. Now let's discuss how exactly are these saccades controlled by our brain. So if you look at this particular hemisphere, this is our central sulcus, the motor cortex. This is our superior frontal gyrus, middle frontal gyrus, and inferior frontal gyrus. So to the posterior aspect of the middle frontal gyrus lies area 8, which is called the frontal eye field. Now the frontal eye field receives information from various regions of the brain, which is still largely unidentified, but pertaining to this topic, it will receive some visual information from 17, 18, 19, and then it gives away the command. Now the command given by the frontal eye field goes through the corona radiata, through the internal capsule, goes all the way to the midbrain, and then it crosses over in the midbrain and then reaches this particular region of the pons. And this is a very, very major player in understanding all of the eye movements, and so it has to be understood what this area is. This is called the PPRF, the paramedian pontine reticular formation, and this is a very important region of the brain. So till here we have to understand that the frontal eye field receives information from the visual cortex and sends information to the PPRF. Now let's see what happens to this information. I'm sure all of us would have at some point of time drawn all of those cross sections of the brainstem at different levels. So if you've drawn a cross section of the pons, you will know that there is a structure called the reticular formation, which I used to just represent with these small dots lying all over the pons. But a part of this reticular formation, which lies throughout the pons mainly, but mainly in the paramedian region. If this is the median plane, just lying paramedian is the paramedian pontine reticular formation, which is usually represented with these two small circles lying just next to the midline. And this is very important in all eye movements, so it has to be known. So the one thing that we have to understand about the paramedian pontine reticular formation is that it likes being the center of attention. It likes it when all eyes are on it. So when a PPRF, when there is stimulation of the paramedian pontine reticular formation of one side, it causes the eye to look towards the side which is stimulated. So if in case the left paramedian pontine reticular formation is stimulated, the eyes will turn towards the left. So our PPRF, extremely attention seeking, causes the eyes to look towards it. So that is something we need to know about the paramedian pontine reticular formation. So going back, you have to understand that our frontal eye field, if it causes stimulation of the opposite PPRF, it will cause the eye to look towards the opposite side. So our PPRF likes the attention, but our frontal eye field wants the eye to look towards the opposite side. Our frontal eye field is a little shy. It wants the eye to look away, but our PPRF wants the eye to look towards it. So this is a very important concept. So the control of our saccades seems pretty clear over here. It's basically just initiated by the frontal eye field, sending information to the opposite side, PPRF, causing the eye to suddenly shift its visual target from one target to another target, suddenly, rapidly conjugate eye movements to look from one target to another target, causing saccades. So this is quite simple. Alright, so speaking about saccades, I did tell what happens when the target is lying horizontally. That is, if Cindy sits next to me, I told you how the PPRF takes care of the movement of the eye. Now what happens if my target is lying vertically? Let's say Cindy is dangling from the roof. Now you have to understand that all of these are real life circumstances. I'm not making all of these up. So this actually happens. So let's imagine that Cindy suddenly came and started dangling on top of my head. Now I have been looking at my book till now, and suddenly I want to shift my gaze to Cindy, who's above my head. That is vertically above. So how does this saccade occur? So our PPRF is controlling horizontal eye movements. So who exactly controls the vertical eye movements? So here it is. This looks like a very complex picture basically, but just to give a very short introduction, this is our pons over here, this is our medulla, and this is our midbrain. So all of you might have heard about this very famous structure, the medial longitudinal fasciculus. Now, we usually tend to hear about the medial longitudinal fasciculus in terms of INO, which we will be speaking about later. But just to give a short introduction to this particular fasciculus, it is composed of many tracts, both ascending tracts and descending tracts, and it actually extends all the way from the midbrain, that is the rostral part of the brainstem, all the way till the cervical spine even. It goes all the way down, but usually the concentration lies only in this part when we speak in terms of INO. So the most cranial part of the MLF, the medial longitudinal fasciculus, has this particular nucleus. It's called the rostral interstitial nucleus of the medial longitudinal fasciculus, the RIMLF, the rostral interstitial nucleus of the medial longitudinal fasciculus. And this particular nucleus, which lies within the midbrain, controls vertical saccades. So the frontal eye field also sends information to the rostral interstitial medial longitudinal fasciculus, and it also sends information to the PPRF, and these are the nuclei which control vertical gaze. So as you can see over here, this within the midbrain also is the third nucleus over here, and the Edinger-Westphal nucleus. So these are the nuclei which take care of vertical eye movements, if you know, supraduction by the superior rectus. All of that is taken care of by the third nucleus. So our RIMLF lies very close to the third nucleus and the Edinger-Westphal nucleus, and it gives information directly to them, causing superior movement of the eyeballs leading to vertical saccades. So this control is by the RIMLF. This again is a very important concept. Now another important structure which is involved in eye movements and saccades is the superior colliculus. Now if you can see this is the optic nerve, the chiasma, and then there is the optic tract. Now visual information through the optic tract goes to the lateral geniculate, and then it goes via the optic radiation to the calcarine cortex, but a part of the information is also relayed to the superior colliculus, and this superior colliculus also transmits some information to the PPRF and the RIMLF, also taking part in saccade production. This is important as well. Alright, now coming to another very interesting concept, it is the concept of neural integrators. Now going back to my story where I'm sitting on a sofa and I'm reading a book. Okay. Now let's say Cindy came and sat again next to me. Now you have to understand that if my cat comes and sits next to me like this, I will continue to look at her for a long duration, like for an hour or so. So you have to understand that to continue to look at Cindy for a long duration, the lateral rectors of this eye and the medial rectors of this eye will have to remain contracted in that exact position for that duration. This requires a lot of coordination. I cannot just, look at her, look here, look here, look here. So if I have to continue to look at her for this prolonged duration, I need a lot of coordinated activity happening in my brain to look to that my extraocular muscles remain in the state of contraction that I want them to be in. So how exactly does this happen? So going back to our PPRF, so it has been noted that the paramedian pontine reticular formation has two types of neurons, called the burst neurons and the pause neurons. So what basically happens is that when PPRF is stimulated, the burst neurons will give out an impulse, and this causes movement of the eyes to the same side. Now what the pause neurons do is that it looks to that the burst neurons don't overdo their work. So it pauses the activity of the burst neurons so that there are no extra saccades. So this is what the pause neurons do. Now there is another set of neurons present around the hypoglossal nucleus. So this is a hypoglossal nucleus present within the medulla, and in the perihypoglossal nuclear region there is this nucleus called the nucleus prepositus hypoglossi, or the NPH, and within this is the step neurons. So what do the step neurons do? The step neurons are required to slowly control the activity of the burst neurons in such a way that the patient is able to maintain lateral gaze. So in other words, the burst neuron will cause the person to look laterally, and the step neurons look to that the burst neurons continue to fire in the exact amount required to maintain this particular lateral gaze. So the activity of the step neurons is further controlled by another system, which is known for coordinating, which is known for being a very strict supervisor, and that is the cerebellum. So what the cerebellum does basically is that it looks to that the PPRF gives discharges just enough to keep the extraocular muscles contracted in just the right amount. So this entire perfection is taken care of by the cerebellum, and the cerebellum forms one of the neural integrators, which looks to that the exact amount of neural discharges are coming out of the PPRF to keep the eyeballs in the exact intended position for the exact amount of time to look at my visual target. So there are other neural integrators as well. For horizontal gaze, we have the cerebellum, of course, which is the main neural integrator, which strictly coordinates the activity of the PPRF. So what the cerebellum does is that it gives away information to NPH and medial vestibular nucleus. So the NPH is basically a group of neurons lying around the hypoglossal nuclei. The medial vestibular nucleus is one of the vestibular nuclei. These receive information from the cerebellum and then give away information further to the PPRF and control the activity of the PPRF very strictly. Now the same thing when we come to vertical gaze, we know the RIMLF is taking care of the vertical gaze as such, but to control the activity, the exact precise activity of RIMLF is the interstitial nucleus of Cajal. Now this controls the exact amount of discharge required from the RIMLF to bring about vertical gaze. So now all of these together act as the integrators required for maintaining precise gaze. Now why is it important that we understand the concept of neural integrators is because if something goes wrong with these neural integrators, our gaze, our conjugate gaze or disconjugate gaze or whatever gaze of both the eyes will not be precisely controlled, and that leads to different eye movement abnormalities. For instance, let's say the cerebellum is not functioning well. Now if in case the cerebellum is not functioning well, our PPRF is still functioning. It's going to cause the eyeballs to look towards Cindy. But since our cerebellum is not here to look to that it is continuing to discharge perfectly, what happens is the eyeball cannot stay in that perfect lateral gaze that is required. So it will tend to move back to its resting position. It will tend to move back anteriorly. It won't be able to maintain this particular gaze that is required because my cerebellum is not keeping the right activity from the PPRF going. So that's why my eyeball is not continuing to maintain this gaze. It will keep going back to its resting position, and that is why the person will have a nystagmus. We will be coming to that a little later. Alright. Now this is a very important picture for supranuclear control of gaze, but we will just be speaking about a part of this picture right now. We will speak about whatever we have understood till now. So if we can see over here, this is the left frontal lobe which has the frontal eye field. So it has given information which is crossed over in the midbrain and gone to our PPRF, and the PPRF is going to give command to the 6th nerve nucleus, which will cause the eyeballs to look here. It also gives information through the medial longitudinal fasciculus to the opposite side 3rd nerve, which will contract the medial rectus. In essence, the PPRF is stimulated and it will cause the eyeballs to look to the right side in this case. And also at the same time we have the cerebellum giving information to the NPH and vestibular nucleus, which will also control the PPRF, and all of these together will look to that the eyeballs look to one particular direction and continue to look to that particular direction without any nystagmus. Now all that is fine. Now going back to my story, I'm sitting on my sofa and I'm reading a book, and let's say Cindy starts running away or moving away. Alright, I have a moving target and I want to continue to look at Cindy as she is moving away. So I don't have a stationary target. It's not that I am shifting my target from one to another. I have my target, which is Cindy, but my target is moving away. I have a moving target. In this case, how exactly are my eye movements controlled? Now, this particular eye movement wherein I am trying to keep my eyes fixed on a moving target is called pursuit. Now, pursuit is basically a slow, continuous, conjugate eye movements. In other words, I have a slow moving target and both of my eyes are moving with the target to look to that particular target remains in focus. It is a slow movement, it is a continuous movement, and it is conjugate eye movements with a moving target. Now it is smooth. Now this will continue to be smooth until around 30 degrees per second. If the moving target is moving at a rate of 30 degrees per second, if Cindy continues to move only till 30 degrees per second, will I be following her up with a smooth pursuit. If in case it's a faster target, if she decides to run at like super fast like flash, then my pursuit will be broken up into multiple saccades. It won't be a smooth pursuit, instead it will be a saccadic pursuit. Now this particular eye movement, the pursuit, is not present at birth and it comes at around 6 weeks of age, and there is a latency of around 120 milliseconds. Now let's speak about the control of pursuit. Now this is a little different from what we see in saccades, and let's see how. So in this case, my moving target is Cindy walking away or running away, and this particular visual information is conveyed to my visual cortex. Now from my visual cortex, this information is transferred to the center which is important for this particular eye movement, and this is the parieto-temporo-occipital junction, the PTO, and also the middle temporal. This is the middle temporal gyrus, posterior part of the middle temporal gyrus along with the medial part of the superior temporal gyrus. All this region has been implicated in control of smooth pursuit. So our visual cortex sends information to MT, the middle temporal, medial part of superior temporal, and the parieto-temporo-occipital junction, which is the control center. And this information is also transferred to the frontal eye field. There is some sort of information relay from the frontal eye field as well. So the information which has been received in this particular region is then transmitted to the next important player in smooth pursuit, which is the dorsolateral pontine nucleus. The dorsolateral pontine nucleus. Now the dorsolateral pontine nucleus is more of a relay center. It doesn't have much work. It just basically gets all of this information from different areas and transmits this information to our cerebellum. So what happens to this information after it reaches the cerebellum? So here again, like in the previous picture, the cerebellum then sends over information to our NPH and vestibular nucleus, which then sends it over to the PPRF region over here and causes the eyes to look towards the same side as the stimulated PPRF. So in this case, if the right PTO is stimulated, it will eventually end up stimulating the same sided PPRF. There is double crossing of information, and eventually the same side PPRF is stimulated. In other words, if my right PTO is stimulated, I will end up looking towards the right side. So if Cindy is walking away towards my left side, my left PTO will be taking care of the left-sided movements. The same side movements are taken care of by the same hemisphere in case of smooth pursuit. We will now be speaking about the next normal eye movement, which is the vergence movements. What are these vergence movements? Now, vergence basically refers to disconjugate eye movement. That is, both the eyes do not move in the same direction. Instead, they move in opposite direction. This can either be convergence, that is, when the eyes look towards each other, or it can be divergence if the eyes look away from each other. Now, these are also slow eye movements and they occur at 20 degrees per second, and the latency is around 160 milliseconds. So the main control for vergence movements, again, it's not very well understood, but the main control lies within the periaqueductal gray matter. This is the midbrain, if we can see. This is the tectum, and this is the region within the tegmentum where the oculomotor and Edinger-Westphal nuclei are present. And this region is called the pretectum, just pretectum. So this particular area controls vergence movements, and it gives away impulses to the or information to the oculomotor and Edinger-Westphal nucleus, which take care of the convergence or divergence of the eyeballs, leading to vergence eye movements, which are also normal. Now speaking about the next normal eye movement, which is the vestibulo-ocular reflex. What is this vestibulo-ocular reflex? Is basically it is stabilization of gaze during head movements. Now for instance, if I am looking at Cindy and Cindy is stationary, she is just sitting in a particular position, but I am moving my head up and down, or I'm nodding my head or moving sideways saying yes or no, and I continue to look at Cindy. Now this particular stabilization of the target, even when I'm moving my head, is taken care of by the vestibulo-ocular reflex. The information from head movements is received by the utricle, saccule and the semicircular canals. Now the other thing that the semicircular canals do is they can also push the eyeballs in different directions. So it has been seen that the horizontal semicircular canals, there are three semicircular canals, the anterior, the posterior and the horizontal. Now the horizontal semicircular canals bring about horizontal eye movements. They push the eyes to the opposite side. So what happens is, if in case my left horizontal semicircular canal is stimulated, it will push both my eyes to the right side, to the opposite side. That is what the horizontal semicircular canals do. Now what the anterior semicircular canal does is, it pushes the eyes upwards. The posterior semicircular canals pushes the eyes downwards. So these are the different eye movements brought about by these different semicircular canals. Now in case, let's just say I'm looking at Cindy, she's sitting in a particular position, but I am nodding my head and looking and pushing my chin downwards, which means my eyeballs are together going upwards to continue looking at Cindy. In this case, what happens is my anterior semicircular canals will be stimulated so that my eyeballs will actually go upwards. So this is basically the idea of vestibulo-ocular reflex. So this has a very short latency, and the speed is around 300 degrees per second. So here, as you can see, we have our vestibular nuclei, which is lying somewhere over here. So our information from our utricle, saccule and semicircular canals is going to get transmitted to the vestibular nucleus, which has a connection with the PPRF, and it also has connection with the RIMLF. It also has connection with the rostral-interstitial nucleus of the medial longitudinal fasciculus, and it controls both of these structures and causes eye movements to various directions. And finally, coming to the last normal eye movement, the optokinetic nystagmus. So basically the optokinetic nystagmus comes into picture when we have a moving environment. So for instance, if you're sitting in a train and the surroundings is moving past you, so initially you will fixate on a particular tree and then it goes back, you'll continue to look at the tree, but when the tree moves out of your vision, you then fixate on the next object and you continue this particular cycle. And this particular cycle is brought about by the optokinetic nystagmus. So there is slow pursuit of the target, and then there is a saccade which causes refixation on a new target. So slow pursuit of one tree and suddenly there's a saccade which will cause fixation on the next tree. So this is optokinetic nystagmus. So over here, as you can see, the slow pursuit of target component is taken care of by the PTO and the saccade is taken care of by the frontal eye field. So one thing you have to notice over here, let's say the object that we were seeing, it was going towards the right side like this. So our right PTO started working and it caused movement of our eye to the right. Now suddenly there is a corrective saccade, which means we have to look suddenly to the left before refixating on a different object. So to go towards the left side, again it is the opposite side saccade, so it will be our right frontal eye field which is causing the eye to move suddenly, the saccade, to the opposite side. Now in other words, the optokinetic nystagmus in one particular direction will be completely taken care of by the same hemisphere. The slow pursuit of it will be the right PTO and the opposite sided saccade will be the right frontal eye field. So one hemisphere itself will be taking care of the entire optokinetic nystagmus. So to test optokinetic nystagmus, I'm sure all of us would have seen this optokinetic nystagmus testing drum wherein it keeps rotating. So we will fixate on one of these bars, and once it goes out of vision, then we fixate on the next bar. So this is how our optokinetic nystagmus is tested, wherein there is slow pursuit of this bar followed by a corrective saccade in the opposite direction. So finally, coming to this very important part of eye movement control, we have been speaking so much about PPRF causing the eye to turn towards itself, the medial longitudinal fasciculus. Now let's see what exactly the connections between these structures are. So basically, the paramedian pontine reticular formation is a very important player in eye movements, as we've already noticed. So what it does is it gives information to the ipsilateral sixth nerve. Alright, now this sixth nerve basically causes this particular eye to look in this direction, in the same direction. Now this nucleus is connected to the third nucleus by the medial longitudinal fasciculus. So medial longitudinal fasciculus basically connects the third nerve, the sixth nerve, the fourth nerve, the vestibular nuclei and multiple other nuclei along the brainstem. So what it does basically is it carries information from the sixth nerve to the opposite sided third nerve nucleus, which gives information to the medial rectus, which causes this eye also to turn towards this side. So this is what this particular structure is important for. So with that, we come to the end of normal eye movements and to the end of part 1 of nystagmus. So thank you. This is basically our teacher for the day, Cindy, saying go away.